The integral of x over 7 times the square root of 49 plus x squared dx falls under a trig substitution type. Because of the plus sign and the square root of 49, we can substitute x equals 7 tangent theta. The derivative of that is 7 secant squared theta d theta. Back to the original problem, replace your x's with 7 tangent theta, dx with 7 secant squared theta d theta. That gives us 7 tangent theta over 7. You can cancel the 7's, times the square root of 49 plus 7 tangent theta quantity squared, times dx, which is replaced with 7 secant squared theta d theta. Under the radical, 7 tangent squared quantity, 7 tangent theta quantity squared is 1 plus tangent squared theta. If we factor out a 49, that leaves us with the square root of 49 times 1 plus tangent squared theta, which is, by Pythagorean identity, secant squared theta. Back to the beginning, I'm going to regroup with tangent theta and secant squared theta together. Under the radical, we've simplified, so tangent theta secant squared theta times the square root of 49 secant squared theta d theta. Taking the square root, that gives us 7 secant theta. The 7 that's currently out here from that 7 times the 7 we get from square root of 49 makes that 49 out front. Then we have tangent theta, secant squared theta, and this leftover secant from the square root. Well, that gives us tangent. There's a total of 3 secant thetas here, but because the derivative of secant is secant tangent, I'm going to hold off on these two terms here. So I'm going to let u be equal to secant theta. The derivative of that substitution is secant theta tangent theta d theta. So this ultimately becomes 49 u squared, and then these terms become our du. Taking the antiderivative, that is u cubed over 3 times 49, that's 49 thirds u cubed. Putting secant theta back in for u, that's 49 thirds times secant theta quantity cubed. Back to our substitution and diagram. Our substitution, x equals 7 tan theta, tells us that x over 7 is equal to tangent theta. Construct a right triangle, mark a vertex with theta. Tangent is opposite over adjacent. Using Pythagorean theorem, we can get the hypotenuse. Now, with secant, that's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. And that's where this square root of x squared plus 49 over 7 comes from. Don't forget it stays cubed. In this example, we have the integral of 2x squared over 4 plus x squared quantity squared. Like the last problem, we have a plus sign of squared plus x squared. So it's logical to try a substitution of 2 tangent theta. And that's what we do here. So we're going to let x be equal to 2 tangent theta. The derivative is 2 secant squared theta d theta. Back to our original problem. Replace these two x's with 2 tangent theta. Replace dx with 2 secant squared theta d theta. Cleaning up, that gives us 4 tangent squared theta times 2 is 8, times this 2 makes a total of 16 in the numerator. Tangent squared theta, secant squared theta. So nothing gained, nothing lost. On the next step, I want to take this denominator. 2 tangent theta quantity squared is 4 tangent squared theta. Plus 4, that tells us we can factor out a 4, leaving 4 times 1 plus tangent squared theta, all still squared. Remember, the original denominator is squared, so all of it's still squared. 1 plus tangent squared theta can be replaced with secant squared theta. So we have 4 secant squared theta squared makes 16 secant to the 4th theta. Simplifying, we can cancel the 16s, and we can also cancel 2 of the secant thetas. 2 from the top, 2 from the bottom, and that leaves us 2 in the denominator. Since secant is the reciprocal of cosine, 1 over secant squared theta can be replaced with cosine squared theta. And that's on this level. We have the integral of, let me scoot that back down a little. There we go. We have the integral of tangent squared cosine squared theta, d theta. Tangent is using a quotient identity as sine over cosine. So tangent squared theta is sine squared theta over cosine squared theta. Multiplied with this, cosine squared over to the side, we can do a direct cancellation, leaving sine squared theta d theta as our integral. In class, we looked at using a power reducing formula, and it comes from the half angle identities. Sine squared theta can be replaced with 1 minus cosine 2 theta over 2. If you need to see the formula, if you don't have a copy of it from class, that's fine. Go to Google, search power reducing formula of sine squared, look at images, and I'm sure there'll be an identity that shows that. You can also find this in your e-text on WebAssign. Splitting this fraction, we can call that 1/2 minus 1/2 cosine 2 theta, and we can also split these integrals up. So we got the integral of 1/2 d theta minus 1/2 integral of cosine 2 theta. Because this angle has a derivative of 2, we need to make sure there's a 2 present and rebalance with 1/2 before we take the antiderivative. The antiderivative of 1/2 is 1/2 theta. The antiderivative of 2 cosine 2 theta is sine 2 theta. These two halves make a 1/4. Because our original substitution involves a single angle theta, we need to modify the sine 2 theta. That's using a double angle identity. You can replace sine 2 theta, and this comes from your trig identities, with 2 sine theta cosine theta. Sine 2 theta is equal to 2 sine theta cosine theta. Now, going up, we've got everything in terms of a single angle. We'll go back up and look at our substitution. The original substitution was 2 tangent theta. Solving for tangent theta, we get x over 2. Tangent is opposite over adjacent. Using Pythagorean theorem, we can get our hypotenuse. Also note that since x over 2 is equal to tangent theta, if you invert, tangent inverse of x over 2 is equal to theta. And we're going to need that in our antiderivative. Okay, going from black to magenta, 1/2 theta is 1/2 tan inverse x over 2. And we covered that just above, right here, under the triangle. Minus the 2 from the 2 sine theta, cosine theta identity will cancel into that 4 twice, so that leaves 1/2. Sine theta times cosine theta using our right triangle. Sine theta is x over root x squared plus 4. Cosine of theta is 2 over square root of x squared plus 4. So we'll put those next to each other right here. That's sine times cosine. Simplifying, that 2 and this 2 from the half will cancel. And we get a reduced answer of 1/2 tangent inverse of x over 2 minus x over these two matching radicals. You just take off the radical, x squared plus 4. plus our constant of integration. Now we've returned it into terms of x, which is where our problem started. In our next example, we have the square root of 16 minus 4x squared dx. Excuse me. Our original problem, we can factor a 4 out from the radicand, and that leaves 4 times 4 minus x squared. If you square root each one terms separately, you get 2 and square root of 4 minus x squared. Because of the subtraction and the constant coming first, our substitution for trig sub will be 2 sine theta. Derivative is 2 cosine theta d theta. Coming back to the original problem, we still have this 2 out front. Replace x with 2 sine theta, dx with 2 cosine theta d theta. So that gives us under the radical 4 minus 4 sine squared theta, which if you factor out the 4 is 4 times 1 minus sine squared theta. 1 minus sine squared theta becomes cosine squared theta. So this radical term, when expanded, factored, and rewritten with a trig identity, becomes 4 cosine squared theta. The 2 from 2 cosine theta, I'm going to marry it with the 2 out front. That gives us a total of 4. Cosine theta d theta, let's follow that down. The square root of this term is 2 cosine theta times this cosine theta gives us 2 cosine squared theta. The 2 from the radical coupled with the 4 out front gives us this 8. Using a power reducing formula, again that comes from your half angle identities, cosine squared theta can be rewritten as 1 plus cosine 2 theta all over 2. And again, you can check out Google search, or you can look in our Google Drive folder, and there should be some power reducing formulas. I know for certain there's some in our e-text, but again, feel free to use Google. This is a power reducing formula. It lets you rewrite a square as a single power. Like we did in the last example, we're going to split this fraction up into a half and a 1/2 cosine 2 theta. Underneath, that's 8 times, splitting the integral, we have the integral of 1/2 d theta plus 1/2 cosine 2 theta d theta. The derivative of 2 theta is 2, so in green I've marked 2, rebalanced it with a 1/2. The antiderivative of 1/2 d theta is 1/2 theta, plus 1/4, the antiderivative is sine 2 theta. Distributing the 8, that's 4 theta plus 2 sine 2 theta. Again, using a double angle identity, sine 2 theta is the same as 2 sine theta cosine theta, which will get us to 4 theta plus 4 sine theta cosine theta plus c. Going back to the original substitution, we substituted in x as 2 sine theta. X over 2 equals sine theta. So sine inverse of x over 2 is equal to theta. We're going to need all that. From this substitution, you can construct a right triangle, mark a vertex with theta. Sine is opposite over hypotenuse, so x and 2 are your opposite and hypotenuse lengths, respectively. Using Pythagorean theorem, your other leg is a square root of 4 minus x squared. Oh, also here, I wrote that power reducing formula in purple, and that's to go from this step to that step. Here it is in purple. Okay, our antiderivative at the bottom was 4 theta. Theta, we're going to replace it with sine inverse of x over 2. So that's 4 times sine inverse of x over 2. Plus, now let me go back down. we have 4 sine theta cosine theta. Using our right triangle, sine theta is x over 2. Cosine theta is square root of 4 minus x squared over 2. These 2's on bottom make a 4, which will cancel that 4 out front, leaving us with a final antiderivative, and it's cleaned up. 4 sine inverse of x over 2 plus x times the square root of 4 minus x squared plus c. In our last example, we have the integral of 1 over x times square root of 4x squared plus 81. Rewriting the terms under the radical as a set of perfect squares, we write that as 2x quantity squared and 9 quantity squared. Bringing over here for our substitute, because of the addition, we're going to use tangent. 2x is equal to 9. Notice those were our squared terms from the original problem. 2x quantity squared, 9 quantity squared. 2x equals 9 tangent theta. Dividing both sides by 2, that's x equals 9 halves tangent theta. The derivative is 9 halves secant squared theta d theta. Coming back to the original problem, we replace this x with 9 halves tangent theta. This dx we replace with 9 halves secant squared theta d theta. That's all done here on this step. All the x's and the dx have been replaced. The 9 halves on the bottom and the 9 halves on the top will cancel each other. Under the radical, after you do the substitution, you have the square root of 9 tangent theta quantity squared, which is 81 tangent squared theta, plus 81. Under the radical, we'll be able to factor out that 81, leaving tangent squared theta plus 1. Rewriting this with secant squared theta, eventually we get 9 secant theta under the radical. So let's put the brakes on a little bit because we've got a lot more to go. We still have this tangent on bottom in front of the radical, and we also have this secant squared on top. So there's a lot to keep up with. Make sure you haven't gained or lost anything. Okay, I think we're ready to make some cancellations. Okay, so we've still got secant squared theta d theta on top. Tangent theta on bottom. This becomes 9 secant theta. 9 secant theta from the radical. Cancel a secant theta from top and bottom, and that leaves a secant theta on top, a tangent theta on bottom. We've got a much nicer and more simplified fraction. Let's see if we can do better than this fraction of trig terms. Secant theta is 1 over cosine theta. 1 over tangent theta, which is written here in blue, because tangent's in the denominator, I have to write it as secant times 1 over tangent theta. Using a quotient identity, the reciprocal of tangent is cosine over sine. We can cancel the cosine, that leaves 1 over sine, which is cosecant theta. So this fraction simplifies to cosecant theta. It doesn't have a very friendly antiderivative at all. In fact, the antiderivative for cosecant theta is natural log absolute value cosecant theta minus cotangent theta plus c. And don't forget this 1/9 out front. Let's go back to our substitution. Solving for your trig function, tangent theta is equal to 2x over 9. That's your opposite and adjacent lengths, 2x over 9. Pythagorean theorem will tell you your hypotenuse is the square root of 4x squared plus 81. Going back to our antiderivative in terms of theta, we had 1/9 times the natural log of cosecant theta minus cotangent theta in the absolute values. Using our right triangle and our trig ratios, cosecant theta is hypotenuse over opposite. Hypotenuse over opposite. Cotangent is adjacent over opposite, 9 over 2x. So now we've changed our trig terms back to terms of x using this right triangle. If you want to combine into a fraction, you can. 2x is your common denominator. So you would have this radical term minus 9 as your numerator with a common denominator of 2x. Hang on to your 1/9 and don't forget your constant of integration plus c.